Hello, and thank you for the introductions. So as you heard and know already, our topic today is how Kubernetes can help building portable applications and move them between different environments.
So this is Terry. Just a brief introduction on Kublr and who we are. Kublr has built a solution for deploying, running, and managing Kubernetes clusters. The solution adds security, logging and monitoring, backup disaster recovery, and configuration management capabilities across cloud, multiple clouds, and on-premise environments. So we thought this topic today, application portability, would be good for people that may also be interested in Kublr, because Kublr is a solution that allows you to deploy your container clusters where you want to. And Oleg will talk a little bit about some of the reasons for that. It's not a Kublr presentation, but he will mention the fact that when he deploys applications both to AWS and Azure in this presentation, he's already set up those container clusters using Kublr, before he does the demo. Back to you, Oleg.
Okay, thank you, Terry. So now to our topic at hand. One of the first questions we may ask ourselves is what are actually the reasons to build portable applications? Because in many cases, a company may be satisfied with the environment they work in, AWS. Why should we move to Azure, for example, or support on-prem deployments? And while this is a reasonable consideration, there are also legitimate reasons to build applications the way they can move between different environments. Some of them are mentioned on this slide. Cloud bursting, one of them. For example, you may have core of your, you might process core of your load, or most of the time your request will be processed in your data center, but sometimes you want to process peak load in the cloud. Disaster recovery may require, or disaster recovery strategy may involve recovery in a different region or in a different cloud, or you may host your application in the data center, but then recover in case of failure into a cloud. And other legitimate reasons mentioned on these slides. Having said that, I want to also mention another thing related to application portability. So as many other things in life, application portability is two-way street. Not only environment should be suitable for porting, so essentially environments should be compatible enough to move application between them, but application should also be designed correctly in a way to support portability. So I want to briefly go through some principles and best practices and leave that behind and then move to Kubernetes. So one of the best summarizations of best practices for portable applications I saw is in 12-factor app manifesto. Some of its statements are very relevant to building portable applications, and as I mentioned here, explicitly declaring and isolating dependencies is probably the most important one. Storing configuration is in the environment also important one, so you can keep your application unchanged when you're moving between environment, just adjusting the configuration. Making sure that application treats backing services as attached resources, meaning that application itself can recover when a resource or service detaches and then reattaches back, and make sure that application can reinitialize service if it is needed. And by service, I mean service in a general sense. Database may be considered a service for your application components. Having said that, so let's move to problems that people face when they are building portable application. Some of the hardest problems and most frequently seen problems that are there when you're moving application from one environment to another are handling increased traffic, especially HTTPS and SSL certificates, handling routing and load balancing, and state persistence. Some applications rely on databases, others require shared file storage or reliable block storage, and making sure that we can satisfy these needs in different environments is a key to ensure that your application may be moved. Messaging is another area that we may consider, although we won't focus on this as much in this presentation. To show it in a diagram, you can see here an application and various needs that may have when it's moving between platforms. And those needs, different platforms may satisfy those needs in different ways. So you may have, so to say, rich platform, a platform which can provide everything that your application needs, or sometimes you can see a not so rich platform which just implements few of application services or resources it needs. Or even sometimes you may see a platform that may be considered poor, which only provides basic needs of the application. And it's difficult to imagine a platform that does not provide even that, even exclusive file system. So I'll stop here. And apparently Kubernetes may help to abstract from these needs and to implement your application in such a way that it's easily movable between different platforms. One of the main characteristics of Kubernetes that allow you to do that are, first of all, its extreme ease and flexibility of configuring your components and connecting them with each other. So it almost feels like a Lego block, a Lego set where you can connect your components and external services any way you like. Very important aspect is that Kubernetes has convenient configuration templating tools, namely Helm, so that you can build a package, single package that you don't change, and parameterize it with different values to adjust its specific deployment. And of course, what's important is availability of convenient abstractions and extensible frameworks to ensure that you can unify definitions for ingress traffic processing and persistent storage management. Namely, I'm talking about Kubernetes objects like services, ingresses, frameworks and concepts like ingress controllers, and framework around volumes and persistent volume management. Just to make sure that we understand that the audience may have different level of familiarity with Kubernetes, I'll spend a couple of minutes and 2 or 3 slides to quickly go through this concept and explain how they work in Kubernetes, and then we'll switch to the demo. So first of all, services. That's one of the basic Kubernetes concepts that allows you to provide a single stable endpoint that to access a set of pods or containers running inside Kubernetes cluster. This pod container set is dynamic, so they can be started, scaled up, down, die, be restarted. Service tracks this dynamic set of containers and rearranges routing rules so that clients of this service implemented by the container set don't see the change, essentially. So in other words, service may be considered a level 4 load balancer implemented by Kubernetes for you. Another function of service is to provide external access to pods, access from outside the cluster. Next abstraction is ingress. Ingress is a little bit higher level abstraction which serves similar purpose to service. So it's a level 7 routing rule. So routing rule which tells Kubernetes how external HTTP and HTTPS requests need to be routed into the cluster, into the services inside the cluster. These rules are implemented via ingress controller. So ingress controller is essentially a glorified reverse proxy which runs inside Kubernetes, watches those ingress rules as they are defined and updated by cluster users, and reconfigures itself to ensure proper processing of HTTP and HTTPS requests. There are different implementations of this ingress controller, Nginx-based, HA proxy-based. There may be an ingress controller which manages external reverse proxy like AWS ALB, for example. But what's important is unification of management of these routing rules for Kubernetes users. And the last set of concepts are related to configurability and persistence of your Kubernetes applications. Config map objects and secret objects allow you to store inside Kubernetes metadata database configuration data, which includes secret data like passwords, keys, tokens, certificates, and map them to your pod and containers inside pod, environment variables and files inside them. Objects like persistent volume, storage class, volume claim, and volume are needed to unify management of persistent storage. Persistent volume.
And in that case, Oleg, you're showing storage outside of the Kubernetes cluster, right?
Yes, exactly. So persistent volume is able to abstract various file storage and file sharing systems, NFS mounts, Gluster clusters, Ceph clusters, AWS EBS, and many others, including localhost dir or ephemeral storage directories that only exist for the lifetime of pod. So, having talked about Kubernetes concepts, we'll move to the application we use to demonstrate how they work. We chose WordPress as it should be very familiar to everybody. As you know, that WordPress uses a database as its main storage, maybe MySQL, Postgres. We are using MySQL. And clearly MySQL requires some place to store its data. is shown here on this diagram. WordPress may be set up or may benefit from using shared FS, but to simplify this demo, we are not using it. And of course, WordPress as a site management system requires processing HTTP requests from the outside world, so it gives us a chance to show how ingress traffic is processed in Kubernetes. So this application is formalized in form of Helm package, and I'll talk about its structure for a minute. So this Helm package includes 6 Kubernetes objects. There is, of course, WordPress deployment, and deployment is a Kubernetes object that starts pods. In our case, we'll use just very simplistic deployment use case where we just run one pod and don't scale it. Service, as we talked, services provide endpoints to a set of pods, and this service will provide access to WordPress. Optionally, based on parameters of this package, we will create WordPress ingress rule. And again, optionally, based on parameters of this package, we will also create a MySQL instance running inside Kubernetes cluster with its own service and deployment. Based on persistent options that we provide, we will also create or not create a persistent volume claim for MySQL to make sure that data is persisted. So our demo environment consists of 2 Kubernetes clusters, and as Terry mentioned, they were created using Kublr, but they are completely standard Kubernetes clusters. You can use scopes or kubeadm to this setup to make sure that we have enough differences between those environments. We created one cluster in AWS based on Ubuntu instances, and the other cluster is on Azure, running on RHEL instances. I combined access credentials for both clusters in a single Kubernetes client config file with 2 contexts. So if you see in the command line that we use context AWS, we are working with the first cluster, and if context is Azure, we are working with the second cluster. And our first exercise is to deploy this package in default configuration, where WordPress runs without any ingress rules configured, and it works with self-hosted MySQL, which stores data on Kubernetes empty dir volume. Empty dir means that it's an ephemeral storage provided by Kubernetes, which only survives while corresponding pod it is attached to is alive. So I'm switching to my terminal, and yeah, just a quick distraction. So let's see our clusters dashboards. So this is the one running in AWS. You can see it has 4 nodes. If we dig deeper, you can see operating system it runs on. Right now it's empty, doesn't have anything in the default namespace. And the second one here is Azure cluster. So we have 2 windows open. Running in Azure also has 4 nodes, also empty. So let's deploy our application. So I'm running Helm. I'm using upgrade command, but with install option, which means upgrade or install if the package is not yet installed. I'm telling it the name of the release I'm deploying, the name of the package I wanted to use, and the file with configuration parameters. So let me run this. So in the report, we see that it creates 2 services and 2 deployments, just as we intended. And while it's starting it up, I'm going to show you, first of all, the empty configuration file, and secondly, the Helm package structure. So as we talked about this, you can see here every object is in its own template file. We can take a look at MySQL deployment object, for example. So if you are familiar with the syntax, it is Go template syntax. We have access to those templates to configuration values, default values for those configuration parameters is specified inside the package itself in file values YAML, and we override it with our own values in our own parameter files. As during this deployment we used empty parameter files, we could have omitted it completely. We don't override any defaults for now. And I'm not sure, please let me know if it's difficult to see the font. I can make it bigger.
Yeah, it's a little bit small, but I think you can read it.
Okay, so I'll make it bigger next time we switch here. So let's see what happens in our Kubernetes cluster. So here it is. We see 2 deployments and 2 pods created by those deployments. It looks like they're healthy, all green. We can try to see if our application actually works. The one problem here is that WordPress we just created is only accessible inside the cluster, but fortunately Kubernetes provides ways to access services that are deployed inside the cluster. And one of these methods is port forwarding. So I can map a port of WordPress pod onto my local machine, 8080 port, which I'm going to do. And let's see if we actually started this application. Yeah,
and again, the reason you needed to do that was because you didn't set up English yet, right?
Yes, exactly. So we are going to set up English as our next step. But it looks like application is healthy. We see initialization screen. So all good and well here. What we are going to do next is to enrich our application. So first of all, we are going to use ingress routing or enable ingress routing. Secondly, instead of using empty dir for MySQL data storage, I'm going to instruct Kubernetes to create an empty AWS EBS volume. To do that, I'm just going to provide a different configuration file. Stop port forwarding and running another Helm upgrade command. The only difference from the first one is that I'm using a different values file. Let me run it. Here goes. It created just a few more objects. One new object it created, we can see here, is an ingress rule. And another one I expect to see is, here it is, persistent volume claim. let's see how it affects our application and how it looks like in Kubernetes dashboard. We still have the same two pods running, but not actually running because my MySQL pod is reinitializing because configuration of Helm package was changed and it recreated deployment for MySQL, specifying new attachments for MySQL pod. So deployment killed the previous one and started a new one, which it waits to connect to this persistent volume claim, another new object we have just created. Let's see what's happening with persistent volume claim. Looks like Kubernetes reports that it is bound. If you remember the slide where I talked about persistent volumes, you can see this picture. Pod using its internal object volume connects to a volume claim, which in turn connects to persistent volume. So this multi-stage structure is needed to separate administrators' duty. So administrator of your cluster can create persistent volumes pointing at actual physical storage, and cluster user responsibilities. So cluster user creates volume claims that get attached to actual persistent volume, or depending on configuration of the cluster or volume claim, it may lead to automatic volume creation, as it was in our example. I'm going back to slide one, and just to review the persistent volume that was created for us. You can see it has some machine-generated name, and internally it says that it's backed by an actual AWS persistent volume. Just to make sure you can see it better. I would expect that application is already initialized by this time. So yes, MySQL runs. WordPress is healthy. We can try to access it. And by the way, because we also asked our package to create an ingress rule, it should now be accessible directly on an internet. It has a valid DNS name, and now you can see error establishing database connection. This is because or actually Kubernetes only recreated MySQL database, but it didn't restart the WordPress pod. WordPress only creates a database on start. So this is a slight violation of one of the principles we saw in 12-factor app. WordPress doesn't treat its dependencies as detachable resources. So we'll have to actually delete it so that it has a chance to reinitialize the database. It shouldn't take long. Usually it takes less than a minute. And while it is doing that, I'll present you what we are going to do next. Or actually what we could do next. This slide shows a slight difference from the previous one. So instead of using our own, which was represented by a green MySQL block here, self-hosted MySQL, we could use actually a AWS managed MySQL instance, AWS RDS MySQL instance. To do that, instead of setting up Just a so instead of using this config file where we just set to Helm package enable persistence, we would configure actual database endpoint, in which case our Helm package does not create a MySQL deployment, but instead configures WordPress deployment in a way that it works with that external database. Let's see how our application is. It looks like WordPress is healthy again. It has restarted and supposedly recreated the database. Let's refresh it.
So to recap, you've deployed 2 different versions of WordPress into Azure. AWS. The first one didn't have ingress or persistent storage set up. You modified the Helm file, and the second one did, right?
Yes, exactly. Essentially, when we updated configuration by redeploying Helm file, what happened? Kubernetes restarted the database and configured a new persistent storage for it. So database was restarted empty. But WordPress does not actually verify every time that the database is initialized. So it stopped working, essentially.
Right.
Because
and that's why you said that WordPress isn't really following the 12-factor app guidance on treating dependencies as external resources.
Yes. There are other considerations, though, because we don't often expect databases to be restarted, and checking regularly whether database is initialized or not may be complex or expensive. Sometimes people figure that it's not really that beneficial to exactly follow all the principles, which is okay. Real life is real life. So the next step, the next part of our presentation is actual migration of this application. We will not only change its configuration in one cluster, we're actually going to redeploy the same package with ingress enabled into Azure Kubernetes cluster. But this time, let's imagine that Azure, unlike AWS, doesn't have means to manage block devices. So we cannot ourselves provide reliable, or we cannot provide reliable block device for MySQL to store its data on Azure. This is not so, of course. For demo purposes, let's say it is. And to make sure that we still can deploy our application onto the cluster, into that environment, we will use cloud-native storage framework called Rook. Rook is essentially a Kubernetes adapter of Ceph open source file storage, clustered file storage, which is why you first need to deploy Rook into our Azure cluster. And this is surprisingly a simple thing. Let's switch to console. To my screen. So deploying Rook is just a question of running one YAML file, which creates several objects. So this YAML file is downloaded from Rook GitHub. So they have a number of examples, a lot of documentation about how it's done. We started Rook operator, and let's see if it's actually started. So we see several new pods running in a Rook system namespace. So it consists of actually actual operator code and Rook agents running on every node of our cluster. So Rook gives you ability to manage Kubernetes, Ceph clusters, just the same way you manage other Kubernetes objects. You can create a object in Kubernetes metadata, and Rook will automatically set up cluster based on parameters specified in that object. So as you can see, I have just done that. I created a new namespace Rook, and I created a cluster object also named Rook in that namespace. Now let's see what results. So what happens now in that namespace is Rook operator starting Ceph cluster components. And we'll see here more pods starting. And this looks like it's almost done. So we have Rook API, we have Ceph manager, we have 3 Ceph monitors, and we have OSD processes, 1 per each node. It's up and running. So next thing I want to do is to run an auxiliary pod called Rook tools, which contains all Rook command line, Rook and Ceph command line tools, so that I can use them and see status of the cluster or objects inside that cluster from time to time. So here we can see I just used rookctl status, and we see that it's healthy, up and running. And the last iteration we are going to do before deploying our application is to actually create a storage pool which will host disk for our MySQL created by our Helm package. Again, it's just a creation of an object called of type pool. We name it replica pool. And then we create Kubernetes storage class that is used for dynamic volume allocation inside this replica pool. Let's see how it looks in Kubernetes dashboard. Storage classes. We can see this storage class that has just been created. Again, I'm going to make it a little bit bigger so you can see it easier. The storage class Rook block has a special type, or it actually identifies a provisioner implemented by Rook, and it has a number of parameters. In this case, it's just one parameter identifying for this provisioner in which pool the block device requested with this storage class needs to be created. We still don't have our application running here, but we will change that in just a second. This is, again, same familiar command line, which deploys our package into Azure cluster with different set of parameters. It creates 2 deployments. It creates an ingress for our demo application. It creates services, and it creates persistent volume claim. But this time, this persistent volume claim is, let's see how it looks. This persistent volume claim has storage class specified, which points at the storage class we just created, Rook block. And as you can see, this PVC is already bound, which means that persistent volume has just been created. Yes, we can see it, bound, looks healthy, and we should see our application getting up. I suppose it will take a few seconds for Ceph clusters. Initialization of block devices takes some time. It's a little bit longer than AWS EBS, probably a minute or 2. And while we are waiting for our application to get up, I I'm going to switch to the next slide and mention some other alternatives that you may want to use in different environments for various application needs. You can see here for file system, Rook, we already saw how it works, but there are also similar cloud native storage packages like OpenEBS, for example, or well-known non-cloud native packages that also have adapters inside in Kubernetes code base like GlusterFS, or you can choose to use completely managed cloud provided service like AWS EFS. For database, again, there are managed options like RDS, or you can deploy your own MySQL, Postgres, MongoDB, whatever is required by your application. For ingress, managed services include AWS ELB and various ingresses controllers based on different reverse proxies are available. And same situation is for many other aspects that are important for, maybe important for your applications, like certificate management and messaging.
And when we were talking about this, when we did the dry run the other day, Oleg, we were discussing the idea that self-managed versus or cloud managed versus self-hosted, they're both available to you, and that the recommendation sometimes is to use the cloud managed, but as long as you're abstracting your code correctly, then you don't wind up with dependencies. Is that right? Exactly.
So actually, a recommendation is to use managed services as much as possible, just because it's easier, less risky, and requires less time. But sometimes you just don't have this option, which is why you may want to use self-hosted replacement for them. And this is one of the things you need to remember. Next slide is dedicated exactly to that. So some important considerations need to be taken into account when you are porting your application from one environment to another. First of all, even if those managed services are available in both environments, they may have different functionality and quality of service. Just as an example, different shared file systems may have different POSIX compliance, maybe, for example, a little bit different in different file systems. Another example, if you're talking about EBS, AWS, EBS block devices, they seem like an ideal solution until you learn that they are availability zone local. So if you create an EBS in one availability zone and that zone goes down, even if your Kubernetes cluster is multi-zone, your application will not recover because the block device is left in the zone which is down. So this is what's important to remember as well. Let's get back to our terminal or dashboard and see how our application survives. Looks like it's up and running, and let's verify it. This time the URL is correct. It's WordPress port Azure at demokubler.com. This subdomain points at my second cluster, and yes, we see that our application running on self-hosted MySQL and self-hosted Ceph cluster successfully initialized.
Great.
So this concludes our demo. I'd like to probably summarize some important takeaways that you may consider. So what we looked through, we saw that cloud-native Kubernetes applications are portable if designed correctly, easy to test, experiment, and configure. Kubernetes provides great tools for that. Those tools include Helm configuration templating, Kubernetes abstractions like persistent volume, PVC, ingresses, services, etc. And your very powerful portability tool in your hand is using self-hosted resources where managed resources are not available, making part of your portable Helm package. Also, you need to remember about difference in managed resources between different environments and between managed and self-hosted options. So what we saw how same application was deployed in different environments on AWS and Azure, on different operating systems, with different ingress options, with can be deployed with and without reverse proxy or SSL termination. And we saw how different persistence storage options may be used from ephemeral storage to self-hosted cloud-native storage. Hope it was useful, and we are open to questions and answers.
Yeah, there are a couple of questions here already, Oleg. So, and also anyone else wants to ask a question, please use the question feature in the screen here. But the first one is it possible to share the presentation and the YAML files?
Yes, absolutely. We'll share the presentation, I think, on SlideShare, and the files will be on our GitHub /Kublr account.
Okay, great. Well, thank you. There was Ivan asked, he said, sorry for the newbie question, but are the commands and templates used standard Kubernetes or Kublr related?
Could you repeat that?
Sure. The question was whether or not the commands and templates used, are they standard Kubernetes or are they specific to Kublr?
Oh no, everything here was absolutely standard upstream Kubernetes. So Kublr was only used to set up the clusters, and Kublr actually uses upstream Kubernetes containers and Docker images, so it's fully compatible.
Yeah. Could you talk for a minute about some of the considerations you had when you designed Kublr, given Kubernetes and the desire for application portability? Were there particular architecture considerations you had when you did that?
Yes. So essentially, Kubernetes, as I mentioned, is a great platform for portability. It's a great unifier, so to say. But problem with Kubernetes, as we saw it when we thought about product Kublr, was that it doesn't unify itself, so to say. So there are like multitude of options to deploy Kubernetes, and different options deploy clusters of different quality. So our goal was to ensure that Kublr is focused on setting up Kubernetes in such a way that it's reliable, that you can rely on it, that you can out of the box use it for mission critical deployments. And that defined actually the design choices we made. So we, first of all, we are using upstream Kubernetes images to actually run Kubernetes components to make sure that we can quickly follow very rapid development pace of Kubernetes itself. We set up a lightweight agent on each node intended only to configure Kubernetes components on this node, and then we use an orchestration control center which orchestrates all those agents in a way that they configure Kubernetes correctly, securely, and reliably.
Thank you, Oleg. A couple more questions here. One that Fahad asked was, what about the data? When we switch between the database, is there any smooth migration strategies? So to interpret his question, I think what we showed was that you can deploy an application to multiple environments, and you can have that application portability. But once it's running in an environment, if it has persistent storage and stores a lot of data, then portability becomes another issue for that data, I think is the question, right? And it's a good question.
A very good question, a very important consideration. Portability of application is not the same as portability of data, because deploying applications in different environments is actually much easier task than making sure that data is moved between different environments. And I think it's difficult to answer it in a very generic way, which is applicable to every setup. But I think the most frequently used approach is to set up replication, either synchronous or asynchronous between environments you want to quickly switch from one to another. And it also depends on the volume of data, because of course,
and from a cost consideration, data out in the cloud is sometimes expensive as well. But I guess from a use case perspective, are you looking at disaster recovery? Are you looking at multi-cloud? Are you looking at hybrid? Data portability is also related to the use case, I think.
Mm-hmm. Yeah. Okay. Cloud native storage actually it's not necessarily cloud native, but replicated reliable storage frameworks like Ceph or GlusterFS may be a great help with that, because Ceph as well as Gluster, for example, have this ability to geo-replicate data, and you can just set up them in active-passive or active-active mode, which will solve your problem.
We have a couple other questions here. One is, what is the difference between Helm and kubectl or kubectl?
So kubectl is a command line utility for Kubernetes itself. So it performs basic operations. It creates specific objects or gives you access, shows you specific objects in Kubernetes metadata. Helm is a higher level tool. So Helm essentially takes a number of templates, processes them, converts them into definitions of multiple Kubernetes objects, and then you may think about Helm using kubectl to create those objects or update those objects. Of course, it doesn't really run kubectl. Instead, it just makes equivalent Kubernetes API calls.
Okay. There's another question here on persistent data. The question is, for persistent data, can we use S3 instead of EFS?
Depends on your application, depends on what interface you want to use to access this data, because S3 is accessible over HTTPS, it's a REST API, and EFS is actually a managed file storage service available over NFS. You cannot mount S3 or you cannot mount S3 directly without using external tools. And even if you can mount it, achieving POSIX compliance or things you expect from a normal file system is difficult. With EFS, it's all possible. So they essentially occupy different niches. Interestingly, Ceph, for example, has all capabilities combined. So Ceph allows you to create replica pools and then allocate space in those replica pools, accessible over 3 methods. You can map them as log devices. You can create file system like shares inside Ceph, similar to EFS, and you can create object storage inside Ceph, accessible via S3-like API or OpenStack object storage API.
Great. There was a question on application code changes required when we move the application to Kubernetes? I think that's a pretty broad question, but we didn't really go into containerization too much, right? So the question is really, any application code changes required when we move applications to Kubernetes?
Yes and no. This WordPress deployment, for example, WordPress wasn't adjusted to run on Kubernetes. It's plain old WordPress. But what has been done is that WordPress was installed inside a Docker container. Now, this Docker container, again, was not specifically adjusted for Kubernetes. So this Docker, the same Docker image, you can run on your local Docker or on Docker Swarm, or as in our example, you can run it inside Kubernetes.
Yeah. And Kubernetes does seem to be the default now. Well, Chris and Ryan, I think we're at the top of the hour now.
All right, great. I'd like to thank Oleg and Terry for a great presentation today. I'd also like to thank today's sponsor, Kublr, for providing the D-Zone audience with another great webinar presentation. Lastly, thanks to everyone who joined us today for our presentation. We hope you learned something new today that will help you in your developer career. Have a great day, and we'll see you next time.
Thank you.